In this presentation, we will examine how public spaces can function not only as places for recreation, gathering, and everyday urban life, but also as adaptive flood infrastructure in the face of climate change. The central argument of this lecture is that urban flood protection does not need to rely only on hidden technical systems or large engineered barriers. Instead, public space itself can become part of a city's resilience strategy. Through selected case studies, including Bentham Plain Water Square in Rotterdam, Copenhagen's climate adaptation and cloudburst planning, the Wuhan Sponge City program, and the Big U project in New York, we will see how flood protection measures can be combined with social, cultural, and ecological functions. These examples show that vulnerable urban areas can be redesigned as multifunctional, resilient, and livable spaces. Rather than separating infrastructure from public life, this approach integrates them, allowing flood management, urban design, and community value to work together in the same landscape. The learning objectives of this lecture are organized around three key goals. First, we aim to understand the multifunctional role of public spaces in flood mitigation. This means recognizing that parks, squares, streets, waterfronts, and open spaces can do more than serve aesthetic or recreational purposes. They can also retain, slow, redirect, and temporarily store water during heavy rainfall or flooding events. Second, we explore design strategies for water retention and community safety. This includes thinking about how hydrological performance can be integrated into urban form in ways that protect people while maintaining the usability and social value of public space. Third, we seek to recognize examples of adaptive and resilient urban landscapes. The selected cases show that public spaces can be designed to respond to climate risks while still supporting daily life, identity, and social activity. Together, these objectives position public space not as a passive urban leftover, but as an active and strategic component of climate adaptation. This lecture is built around several key concepts. The first is blue-green infrastructure, which refers to integrated systems of water and vegetation that help manage runoff, support ecological processes, and improve urban environmental quality. The second is sponge city principles, which emphasize storing, absorbing, infiltrating, treating, and reusing rainwater within the urban landscape instead of rapidly draining it away. A third concept is flood adaptive landscape design, which means designing public space in ways that allow it to respond to changing water conditions. In this approach, water is not treated only as a threat to be removed, but as a dynamic force that can be accommodated spatially. The lecture also highlights the co-benefits of these approaches, including recreation, biodiversity, and resilience. This is important because flood adaptive design is most effective when it provides multiple layers of value. A public space that helps manage water while also supporting leisure, ecological diversity, and social interaction is stronger, more useful, and more justifiable in planning and implementation terms. The methods and frameworks introduced in this lecture show that adaptive flood design requires both technical analysis and spatial design thinking. One important method is the integration of hydrological modeling with spatial design. This means that understanding runoff patterns, water depth, flow direction, and retention capacity must inform how public space is shaped and programmed. Another important idea is multi-scalar flood adaptation, which considers flood resilience from the neighborhood scale to the basin scale. Public spaces do not function in isolation, they are part of larger hydrological systems. The lecture also refers to stormwater management tools such as bioswales, rain gardens, and wetlands. These are examples of landscape-based elements that can slow runoff, support infiltration, and improve water quality. Finally, the lecture highlights the role of participatory design in community engagement. This is important because adaptive public spaces are not only technical interventions. They are also lived environments, and their long-term success depends on how communities understand, use, and support them. In this sense, resilient design is both infrastructural and social. The international case studies in this presentation were selected to show different but connected approaches to adaptive flood infrastructure. Rotterdam's Bentham Plain Water Square demonstrates how an urban square can combine public life with temporary stormwater storage. Copenhagen's cloudburst management plan shows how an entire city can rethink public space and surface infrastructure to deal with increasingly intense rainfall. Wuhan's Sponge City program illustrates how large-scale urban adaptation can integrate nature-based and gray infrastructure solutions in order to create a more sustainable water cycle. New York's Big U project demonstrates how coastal flood protection can be designed not only as a defensive barrier, but also as a socially and spatially valuable public landscape. Together, these examples show that adaptive flood infrastructure can take different forms depending on local context, scale, and risk type. However, they all share one important principle. Flood resilience is stronger when it is integrated into everyday urban space rather than treated as a separate technical system. Bentham Plain is presented as a leading example of how public space and rainwater retention can be combined in one urban intervention. The project aims to store rainwater as a way of adapting to climate change while also providing the surrounding neighborhood with a high-quality and multifunctional public space. Most of the time, the square remains dry and is actively used for sports, games, theater, and daily public life. However, during periods of extreme rainfall, the same space becomes part of the stormwater system by storing water and helping reduce the risk of urban flooding. What makes this approach especially important is that it does not treat flood infrastructure as something hidden from citizens. Instead, the infrastructure is made visible and integrated into a space that people already use and value. In this way, Bentham Plain demonstrates that adaptive flood infrastructure can be socially active, spatially attractive, and hydrologically effective at the same time. It is not only a storage area, it is a public landscape with dual function. This slide explains the physical structure of the Bentham Plain project in more detail. The square includes two shallow basins, one deeper basin, and stainless steel gutters that direct rainwater into the storage areas. The system is designed so that runoff is not left uncontrolled. Instead, water is intentionally guided into the basins, where it can be temporarily retained during heavy rainfall. The project is located in an irregular urban space, and this makes it a particularly interesting example of adaptive design because it shows how leftover or difficult urban sites can be transformed into high-performing public infrastructure. The deeper basin can function as a major storage space during more intense events, while the shallow areas also contribute to collection and hydrological capacity. One of the shallow swales includes a plant island, which adds ecological and spatial value to the water management system. This arrangement allows Bentham Plain to operate as a multifunctional infrastructure landscape. It manages water, supports recreation, and creates an educational and visible relationship between the city and stormwater processes. This slide is primarily visual, but it reinforces the core lesson of the Bentham Plain case. The project should be understood not just as a technical solution, but as a design strategy in which form, use, and hydrology are tightly connected. The visual material helps us see how the basins, level differences, circulation areas, and activity spaces work together as one integrated system. In dry weather, the square is experienced as an everyday public environment. During storm events, the same geometry allows water to be captured and held in a controlled way. This transformation is a key principle of adaptive flood infrastructure. It means that cities do not always need separate spaces for infrastructure and public use. Instead, one space can be designed to serve different functions at different times. Bentham Plain therefore provides a strong example of how climate adaptation can be embedded into the identity of a place, making resilience visible and usable rather than hidden and purely technical. Copenhagen's cloudburst management plan is introduced as a long-term strategy for preparing the city for more frequent and more intense rainfall events in the future. The plan is designed to reduce flood risk, reinforce blue-green infrastructure, and provide socio-economically sustainable solutions. Several components are highlighted in the slide. New drainage channels that direct rainwater toward the sea and ports, storage areas such as parks, sports fields, and open spaces, and underground tunnels, especially in densely built-up parts of the city. What is important here is that the city is not relying on a single measure. Instead, it uses a combination of landscape-based and infrastructural responses across different urban conditions. This reflects a systems approach to flood adaptation. The plan acknowledges that dense urban environments need flexible and layered solutions, and that public spaces can play a central role in storing, redirecting, and safely conveying stormwater when conventional drainage systems are overwhelmed. This slide emphasizes that the cloudburst plan is central to Copenhagen's broader climate adaptation strategy. Its significance lies not only in technical flood protection, but also in its ability to improve the quality of urban life. In other words, infrastructure investments are not treated as purely engineering-based expenditures. They are also seen as opportunities to create environmental and social value. Streets, parks, and open spaces are reimagined as part of a citywide adaptation framework. This helps public space gain a stronger strategic role in urban resilience planning. The lecture highlights that the Copenhagen approach integrates technical, social, and environmental benefits. That integration is one of the reasons the plan is influential internationally. It shows that a flood adaptation project can also support better public space, better environmental performance, and better urban livability. The city is therefore designing with water, rather than simply defending against it, and this marks an important shift in climate-responsive urban planning. The Wuhan Sponge City program is presented as one of the major examples of large-scale climate adaptation through integrated water-sensitive design. The slide lists several design tools and landscape elements used in the program, including rain gardens, biofilters, grass swales, wetlands, permeable pavements, rainwater retention modules, and infiltration swales. It also highlights a very important performance goal: retaining, storing, and using 60 to 85% of annual rainfall on site. This target reflects the sponge city logic very clearly. The aim is not to remove water from the city as quickly as possible, but to absorb, treat, and reuse it within the urban environment. In this way, public space and landscape systems become part of a more sustainable water cycle. The Wuhan example is important because it shows that nature-based solutions can be implemented at large scale and in dense urban contexts. It also shows that resilient flood management can be combined with better environmental quality and better everyday urban conditions. This slide reinforces the same core idea by presenting Wuhan as one of the leading examples of China's climate adaptation strategies. The program aims to store, treat, and reuse rainwater through a combination of nature-based and gray infrastructure solutions. That combination is significant because it reflects a hybrid model of urban resilience. It recognizes that large-scale cities often require both ecological and engineered systems working together. The notes emphasize that the program has both reduced flooding and improved the quality of urban life. This is a critical point, because it demonstrates that water-sensitive urban design can deliver multiple benefits rather than functioning as a single-purpose technical intervention. The Wuhan case therefore supports the broader argument of the lecture. Adaptive flood infrastructure is most valuable when it strengthens hydrological performance while also improving the livability and resilience of urban environments. It proves that nature-based approaches are not limited to small pilot projects. They can shape metropolitan-scale urban adaptation. The Big U project is introduced as a coastal protection strategy that combines flood defense with social and cultural functions across Lower Manhattan. The slide identifies several design elements: the elevated embankment called the bridging berm, deployable walls attached to the underside of an elevated highway in the two bridges and Chinatown areas, and the battery berm, which combines an elevated path with a series of upland knolls to create distinctive landscapes. These examples show that the project is not conceived as a single continuous wall in a conventional sense. Instead, it is a sequence of landscape and infrastructural responses adapted to different neighborhood conditions. The project aims to strengthen infrastructure while also meeting the social and cultural needs of local communities through a 10-mile-long protection system. This is a significant design principle because it suggests that climate protection should not isolate neighborhoods or diminish public life. On the contrary, resilient infrastructure can be designed as an urban amenity and as a public realm improvement. This slide explains the territorial scope and strategic aim of the Big U proposal. Developed in collaboration with New York City, the project seeks to protect Lower Manhattan against floodwaters, storms, and other impacts of climate change. The proposed system wraps around the low-lying topography of Manhattan, extending from West 57th Street to the Battery and continuing to East 42nd Street. The scale of the project is important because it demonstrates that adaptive flood infrastructure can operate not only at the scale of a single square or neighborhood park, but also at the metropolitan waterfront scale. At the same time, the project remains closely connected to local urban conditions. It is both a regional protection strategy and a neighborhood-based public realm project. This duality is central to the logic of resilient design. Large-scale flood protection must still respond to the everyday social, spatial, and cultural life of the city. The Big U therefore represents a model of infrastructural protection that is spatially differentiated, publicly oriented, and integrated into urban life. Although this slide mainly provides a visual reference, it helps reinforce how the Big U should be read as a landscape-based resilience system rather than only as a technical coastal defense project. The visual material supports the understanding that embankments, pathways, walls, and landform modifications can all become part of a coherent public space strategy. This is especially important in dense cities, where protective systems must be integrated into existing urban life instead of creating isolated infrastructural edges. The Big U demonstrates that public space can be reshaped to absorb risk while maintaining access, continuity, and neighborhood identity. In this sense, the visual dimension of the project is not secondary. It is part of how the project communicates resilience to the public and how it turns adaptation into a visible and lived urban condition. After presenting the case studies, the lecture turns to planning and implementation links. The first point is the importance of embedding adaptive design into land use plans. This means that flood resilience should not be treated as a separate or occasional design concern. It needs to be incorporated into regular planning frameworks. The second point is linking urban flood management with public realm enhancement. This is one of the strongest lessons from all the case studies. Public space improvements and flood adaptation can be developed together rather than as separate agendas. The third point is policy support through climate adaptation frameworks. Without institutional and policy backing, many of these projects would remain isolated experiments. Finally, the lecture stresses the need for interdisciplinary cooperation among planners, engineers, and ecologists. Adaptive flood infrastructure operates at the intersection of hydrology, design, ecology, and governance. Successful implementation therefore depends on coordination across professional fields as well as across scales of decision-making. The conclusion of the lecture brings together the main message. Adaptive public spaces provide both ecological and social functions, and effective flood resilience depends on integrated, flexible urban systems. In other words, public space should not be viewed only as decoration or leftover land. It can become an active part of flood adaptation by storing, redirecting, absorbing, or slowing water. At the same time, these spaces can continue to serve communities through recreation, mobility, gathering, and ecological improvement. This dual function is what makes them especially valuable in contemporary climate adaptation practice. The discussion questions at the end of the lecture invite students to think critically about design and management. How can flood infrastructure also serve as community space? And what are the main challenges in maintaining multifunctional adaptive areas over time? These questions remind us that resilient design is not only about creating effective forms. It is also about long-term maintenance, public acceptance, governance capacity, and ensuring that multifunctionality remains meaningful in everyday use.